We were able to do some practice solving linear first order and got a good intuition about how it works. Idea, make things look like a derivative on one side, and life is good. But there's still lots of things we didn't have a chance to practice, so we should do more practice. So let's do it! We'll join this problem currently in progress. So as a reminder, what's going on? Well, we have this tank here. It has a capacity of 120 gallons, and initially there's 90 pounds of salt, and it's dissolved in 90 gallons of water. And then some brine comes in. Now, brine is just a fancy way of saying salt water. There's 2 pounds per gallon of salt, and it's coming in at 4 gallons per minute. So if you say, 2 pounds per gallon, 4 gallons per minute, that's 8 pounds per minute. And then it's well stirred, and then there's something flowing out of the tank at the rate of 3 gallons per minute, so that's down here. And so we say, okay, good. Now you'll notice I'm using different colors here, and that's to emphasize that the kind of salt water coming in is different from the salt water going out. Because when it gets mixed in, it might become less salty or more salty depending upon what's currently in the tank. And so it makes the output a little bit more interesting. The input is very straightforward. We know, 4 gallons per minute, 2 pounds per gallon, great, 8 pounds of salt per minute, nothing surprising. The output, that's where the fun stuff lies in this problem. All right, so what's the question? How much salt does the tank contain when it is full? Now, you can work it out. So it turns out, because you have 4 gallons per minute coming in and 3 gallons per minute going out, then lo and behold, the amount of fluid is 90 plus t, because every minute you gain 1 gallon. It's only 120. And so it's really saying when it's full is at time 30. So our goal, find S of 30. So how much salt there is. So S is the amount of salt. Given the salt at time 0 is 90. That's from this 90 right here. And the important part for us, S prime equals 8 minus 3 over 90 plus T S. We should remind ourselves how we got to that differential equation. So there's really 2 parts here. There's the 8 and the 3 over 90 plus TS. You're like, ooh, wow, not profound, Steve. But they're representing 2 different things. So the 8 here is saying what's coming in. Because if I want to know the change, I say, how are things coming in? And that's why we said, we have that easy part. Always we have 8 pounds of salt coming in at a constant rate. No surprises. The other part, the more interesting part, what's going out? So you add the in, subtract the out. Now the problem is it's subtle because it will vary with time as to how much is coming out. So we can't just say, it's this number and that's it. Life is good. Bob's your uncle. Move on. We have to say, how much is going out? So the way we do it is we first off ask the question, what's the proportion of material being removed? And not worried necessarily about salt, just like all the material. So it's a ratio of 2 things. So the numerator is how much leaves. So you'll see that there's 3 here. So that becomes the numerator. So that 3 became that 3. The denominator, so the downstairs, that's how much there is in the tank at the current time. We made a point, there's 90 gallons. Every minute we add a gallon. So there's 90 plus t at time t. So output over how much is left in the tank at time t, that's the proportion of salt being removed. Think of it like a percentage. So like the 3 over 90 plus t might be like 0.15. So it's like, 15% is being removed. And so, all right, but I need to go from a percentage to saying, how much does that translate into the salt? So that's why we have this factor of S. So this is the proportion of the current salt that's being removed. All right. Well, with the hard part done, the setting up, the rest, we follow our process. So, rearrange this. S prime plus 3 over 90 plus t times S equals 8. And this part right here, 3 over 90 plus t, Well, this acts as our, what we were calling p before. So we need to integrate that and then take e to that function. So we'll do that to the side here. So the integral of 3 over 90 plus t dt, well, that's 3 log 90 plus t. Or, if you like, log of 90 plus t cubed. Now remember, when we're finding the integrating factor, we don't need to worry about the plus c. Oh, that's nice. We will need to remember the plus c later on, but that's later on. Okay, so that's not our integrating factor yet, though, right? We have to take e to that. So our integrating factor, what we need to add is e to the log of 90 plus t quantity cubed, which is 90 plus t quantity cubed, because the exponential and log have a nice tendency to undo each other. So what we do here is we take this 90 plus t cubed and we multiply that equation through. So everything gets a 90 plus t cubed. And we'll end up with 90 plus t quantity cubed s prime plus 3 90 plus t quantity squared s equals, and I didn't plan very well for spacing here, but well, that happens, equals 8 times 90 plus t cubed. But through our careful planning, the left-hand side is nice. In particular, this is the derivative here of 90 plus t cubed times s. And now we're like, oh, great, wonderful, wonderful. So we're going to integrate both sides. So we integrate, throw in some little dt's. And when we do that, we'll get 90 plus t quantity cubed times s is equal to, now the 90 plus doesn't really do anything. So you can think of it like t cubed. So it'd be t to the fourth divided by 4. So that would be 2 times 90 plus t to the fourth plus some constant c. Now what we can do is we can solve for our constant here. So we say, look, at time 0, our salt is 90. So we'll get 90 cubed times 90 is equal to 2 times 90 to the fourth plus c. Now, 90 cubed times 90 is 90 to the fourth. And here I have 2 times 90 to the fourth. So you can say that c is minus 90 to the fourth. Now, we don't have to figure out what that number is. I mean, it's a number, but we can just say, look, it's minus 90 to the fourth and be satisfied with that. And now, with our c in place, we're ready. We're ready. So our last little bit of cleaning up here, we'll solve for s. So s, if we divide everything by 90 plus t cubed, we get 2 times 90 plus t. So that's dividing through here. And then c is minus 90 to the fourth over 90 plus t cubed. And so the last thing, now that we have how much salt there is at any given time, is to say, well, plug in our time 30. So our answer, how much salt is in the tank? Well, that's 2 times 90 plus 30 minus, here we'll have 90 to the fourth, and downstairs 90 plus 30, well, that's actually 120 cubed. Now, if we were really interested, we could go and work out that number. I don't know if I'm that interested, though. And so we'll leave it in that form. Okay, great. But just for those skeptics out there, let me go check. I'll come back and join you in a second. All right, so I went and did the check, and it turns out that this amounts to roughly 202 pounds. So 202.03125. And all right, well, does that make sense? We can think about it. So there's 90 pounds currently in there, and at every minute, 8 more pounds comes in. And so if we think, well, okay, 90 plus 8 times 30 is 240. So 330 is an absolute max. Never could be more than 330. So it's good that we aren't above that, or we're not even that close. And so 202 actually is not an unreasonable estimate. It gets us, I think, in the right ballpark. So, well, there we go. One mixing problem down. I'm sure we'll see more today and probably again sometime later in the semester. For this problem, we're asked to find the solution for y prime equals 3 plus y tangent of x, where y of 0 equals 2. And, well, actually, let's think about how we could do this in 2 different ways. And then we can compare, right? Because why not? It's fun to do things in more than one way. So, putting on our hats from a previous lecture, we could say, wait a second, this is separable. So if we think separable, and why not? We'll just do that really quick. What would happen? Well, what would happen is we can say, look, this can be written as y prime is dy dx, and so you can write this as dy over 3 plus y is equal to tangent of x dx. So it separates pretty simply. And now you integrate both sides, and you say, well, this is the natural log of 3 plus y, and the integral of tangent is, of course, as we all know, or as we all can turn our pages over and look on the back, log secant. So log secant plus a constant. And now we get rid of the logs by raising both sides to the e, or really we could say putting both sides into the exponential function. And we get 3 plus y is some constant secant x. Remember that this e to log secant x plus c, this plus c can come down as a multiplicative constant in the front. Technically these c's are not the same. This is like e to the c, but we're like, well, it just becomes like a new constant, so it's like, it's the new c for a new generation. So that's what we have. And so, great. So our answer will be c secant of x minus 3. Well, all right, sure. But what's c? Initial conditions. So we get that 2 is equal to c times secant of 0 minus 3. Well, secant of 0 is 1, so this is c minus 3. So that says, aha, c is 5. So our final answer is 5 secant of x minus 3. Okay. So that's our separable hat. Now let's do it with our new hat. That's right. We have more than one way. And it's one of the fun things. You might say, oh, that sounds terrible because you're not sure what to do. Well, it means that you have options. And, of course, what does it mean to do the right way? Well, there isn't necessarily a right way. The right way is the one that you're comfortable with, and you'll get the right answer. And hopefully that doesn't take too much time. So, how would this be done if we were thinking about this in terms of a first-order linear? So, all right, we'll call this our linear solution. All right, well, what would it look like? Okay, well, first off, we have to write it like a linear solution, or rather linear function. So we do some distributing, and we could say, all right, y prime equals 3 tangent of x plus y tangent of x. And from here, we say, well, move it across because you got to make it, something y prime plus something times y. So minus tangent of x times y equals 3 tangent of x. And now we go through our process. Okay, so this minus tangent of x, don't forget the minus. It's easy to forget the minus, so let's not do it. We're going to be smart right from the very beginning. So this minus tangent of x, this is our p of x. So the integral of minus tangent of x dx, well, the integral of just tangent is secant. So we can write this as minus log secant, but really we can put the minus back inside. So the minus can come in as a power. Secant to the minus 1 power, it's like 1 over secant. And 1 over secant has another cool name. We call it cosine. So log cosine x. So our integrating factor, rho of x, will be e to the log cosine of x, which simplifies to cosine x. So we're going to take that cosine x and we're going to put it up there. Everything's going to be multiplied now by a cosine of x. So we're going to multiply all of this by cosine of x. So we have cosine of x times y prime. Tangent of x times cosine. Well, tangent is sine over cosine, so you're canceling the cosine out. So you get minus sine of x times y. And I don't know why sometimes I put parentheses and sometimes I don't. It's one of those idiosyncrasies. Equals 3 sine of x. But of course, this side, by design, is nice. This is the derivative of cosine of x times y. And you can always double check. Okay, first times the root of the second, good. The root of the first, the root of cosine is minus sine times the second. All right, well, now that we have our nice derivative on the left-hand side, we integrate both sides and we see what we get. So integrate, integrate. Integral of the derivative is our nice function, cosine of x times y. And that is going to be equal to, well, the integral of sine is negative cosine. You got to be really careful here. So minus 3 cosine x plus c. Now, divide by cosine of x, and we're left with the conclusion that y is equal to minus 3 plus, then c over cosine, well, that's c times secant, which is exactly what we had over here. So the rest is the same. So we'll put a dot, dot, dot. Just follow your nose over here, and we come to the same conclusion that we have negative 3 plus 5 secant of x. So both will give you the same answer. So again, do the one that you're comfortable with. Do the one that you will make fewer mistakes on, get the right answer, and hopefully not take too long. Generally speaking, the shorter the process, the less chance for mistakes. Generally. It, of course, varies with person to person. All right. What a fun problem. Our next problem asks, solve 1 minus 4xy squared times y prime equals y cubed. And you're like, Steve, this is in the wrong place. This is not a linear differential equation. Because look at it. You've got y squared multiplying by y prime. You've got y cubed. You should only have a single y prime and a single y, and the two shouldn't be separated from each other. So this is in the wrong place. Well, if we do try to solve it in terms of y, but there's a hint. there's a hint on this one, and it's kind of an interesting idea. It says change the problem. Well, that's fine. We can do that. And what does it mean by change? It says, don't think of this y as a function of x. Think of x as a function of y. Now, what does that mean? So we're really going to have to sort of change our mindset. And I'll tell you, the ideas are easy to say, and the process is not hard, but man, it's so difficult when we're so used to like, oh, y is a function of x, to say, okay, x is a function of y now. And our brain's like, I don't want to do it. Stop. But we got to do it. We got to do it. Okay, so we're going to change our mindset. And now the tricky part, well, what about y prime? What does that do? Well, y prime, you can think of that as dy dx. How does y change with respect to x? X prime would be, how does x change with respect to y? And so what ends up happening is it turns out that y prime is 1 over x prime. And so we make this little small change. We say, all right, this is 1 minus 4xy squared times 1 over x prime. That'll equal y cubed. And we'll move the x prime across. 1 minus 4xy squared is equal to y cubed x prime. And notice that in terms of the x function, there's a single x, there's a single x prime. And there, in some sense, we can put them into a nice linear combination. In other words, by switching our mindset, by changing how we look at the problem, we take it from something that's not linear to something which is. Good times. Great times, actually. All right. So we'll do a little bit of rearranging here. So y cubed x prime plus 4x y squared. Actually, I'm going to write this as 4y squared x because I really want to think of the x's on the end. Equals 1. So I move this across and I just sort of flip left and right. Okay, well, from here on out, it's the same process. The only hard part is keeping it straight up here. So don't stress too much. Just let the math flow through you. We need to make our coefficient of x prime be a 1. So we'll divide through by our y cubed. So we'll get x prime plus 4 over y squared divided by y cubed means there's a y left down there. X equals 1 over y cubed. We'll integrate this part, the integral of 4 over y. dy is 4 natural log y, which is natural log of y to the 4th power, which means that our integrating factor is e to that natural log of y to the 4th. Basically, whenever you see a log, you really want to make it just log of something. So we really want to move that forward, and that's why we keep doing that. So we'll multiply everything by y to the 4th. So that is what's going to happen. So we take our y to the 4th, what we just found here, and we're going to multiply everything there by y to the 4th. And doing that, we'll get y to the 4th times x prime plus 4y cubed times x equals y. The left-hand side, well, this is a derivative with respect to y. Okay, gotta keep track of what variables we're using. Y to the 4th times x. And on the other side, we have y. Okay, so we're rounding the corner here. Our next thing is we integrate both sides with respect to y. And doing that, well, we'll get y to the 4th times x equals 1/2 y squared plus c. And we can be happy with that. If we wanted to, we could solve for x. we really can't solve for y in a nice way. Now, we kind of can, but we're not going to try. Because it's almost a quadratic, but it's so not worth it. It's so not worth it. So we're not going to go down that road. But if we wanted to, at least we could say, look, x is 1 over, when you take y squared divided by y to the fourth, you get a y squared downstairs. I'll say that's 2y squared plus some constant c, y to the fourth. And there we go. That's a perfectly fine solution, you know? This would fall more into our implicit category, y as a function of x, but certainly x is a function of y. We've just nailed it right on the head. Good job, us. Yeah. So our next problem. Solve 1 plus t squared y prime plus 4t times y is 1 over 1 plus t squared squared. Now you're looking at this and like, 1 plus t squared downstairs? Somebody might have a little bit of an unhealthy obsession with arctangent. Huh? Well, that's a topic for another day. But for now, we'll just work the process, right? It's always the same process. Step by step, we work it through. No big surprises. No big surprises. All right. So the first thing is we've got to take what's in front of the y prime and make it a 1. So everything gets divided by 1 plus t squared. So we have y prime plus 4t divided by 1 plus t squared times y is equal to 1 over 1 plus t squared cubed. Now, don't worry too much about the fact that it's 1 plus t squared cubed. We're actually not going to have to integrate that because we have some work to do along the way. If we did have to integrate 1 plus t squared cubed, that might take us a while. But let's see, what do we have? This will be how we find our integrating factor. We're going to use that term. So we need to integrate 4t, divide that by 1 plus t squared dt. So we'll let substitution here, u be the bottom. And so u equals 1 plus t squared. And du would be 2t dt. Oh man, this is so good. So we have a u downstairs. Now upstairs, we have 4t dt, which is twice 2t dt. So this becomes the integral of 1 over u du. Or if you like, that's 2 natural log of u. Now we'll do two things. We'll replace u by 1 plus t squared because, well, u is 1 plus t squared. And then the other thing is we can put the 2 inside. And so doing that, we're going to end up with the natural log of 1 plus t squared squared. Good. Now, the next thing is, of course, we have to take that and put it into the exponential function. So our integrating factor, rho of x, is e to the natural log of 1 plus t squared squared, or if you like, 1 plus t squared squared. And we do like that. All right, so we're going to take that, put it right there. Okay, so updating our equation now, we have 1 plus t squared squared y prime plus 4t times 1 plus t squared, because we cancel one of them down here, times y is equal to, on the other side, well, there's 3 downstairs, there's 2 upstairs now, so that's 1 over 1 plus t squared. And the left-hand side. By design, of course, I keep saying that, but, you know, it's good to see it. 1 plus t squared squared, which is our rho, times y. And take the derivative of that. And on the other side, that'll be 1 over 1 plus t squared. All right. Well, we're in our home stretch now. So from here, what do? Well, we integrate both sides. Because, well, now we're in a place where we can integrate. So the first term, great, easy. 1 plus t squared squared y. And the other side, 1 over 1 plus t squared. Oh, yeah, you know it. We know. We all saw it coming from a mile away. That's arctangent. Arctangent of t. And, of course, don't forget your plus c. So, finally, to solve for y, divide through, and we end up with y is equal to arctangent of t over 1 plus t squared squared plus some constant, whatever suits our purposes, over 1 plus t squared squared. And no initial conditions, so that's it. Our final answer. What a great problem. What a fun problem. So our next problem might hit a little bit close to home. It says the following. There's a 25-year-old ISU graduating senior. I know, you have to leave at some point, and it's wonderful. All right, but anyways, they accept an engineering position with a salary behaving as S of t equals 50 e to the t over 30k. So k is 1,000. So like, and the t is how many years you start after, how many years since you start. So initially it's 50,000, doesn't sound like much, but of course, exponential growth is wonderful. You'll make more and more and more. Now, the graduate has a retirement plan that grows at a rate of 5% continuously, and also 10% of the salary is deposited into the retirement plan. Determine the amount available for the graduate when the graduate reaches the retirement age of 70. All right, good. So we have our question. How much money will I have in retirement? Will it be enough? And how do we figure it out? Well, we can model everything by a differential equation. So what do we have? We need to think about what's behaving. So we have our salary is S of t. Now, this is not the part that's going to have a differential equation. We already know how our salary is behaving. It's our retirement that we're asking about. Our retirement is changing. So let's talk about R of t. This is the retirement account at t years. So, okay, we've given it a name. And what do we know? Well, as with all graduating seniors, when you retire, I shouldn't say all, but a lot of them, there's nothing there at time 0. So your retirement account starts with the job. Okay, so that's our initial condition. What do we want? Well, we want to know how much money there is at age 70. Now notice that the t is how many years after starting. You start at 25. So we want to find, well, okay, 70 subtract 25. We want to find what is in the account in 45 years. Okay. Now the last thing is figuring out how is our retirement account changing. Now in this case, there's no disappearing, it's all going up. But there's 2 different ways it's coming up. So it's important to keep track of it. So let's figure out what our 2 pieces are. So our change in retirement is a combination of 2 things. One thing is that there's 5% compounding interest. We know it because it tells us that it grows at a rate of 5%. Now, 5% means what? Well, that says if you take your retirement account and you take 5%, which is 1/20th, that's how much will be added in the next cycle. Usually think about a year, but because I've compound continuously, it's slightly different. But roughly that's what should be happening. So we have that in our differential equation as 1/20th R. So this part right here is the rate of 5%. So this part corresponds to this part. But there's something else that happens, which is the other interesting part, which is we're going to add 10%. So that's 1/10 of the salary. Now the salary varies with time. So we say, okay, our salary is 50 e to the t over 30. All right, so again, just for reference, the 10% of salary is deposited is this part right here. And why do we have a plus? Well, because there's an and. So the and says there's this and this, so put them together. And of course, sometimes you have to understand context. Plus can be multiplied, but here plus means adding. All right, so great. And now we're ready. And let's figure it out. So the hard part is setting it up in some sense, because among all the first order linear, well, no big surprises, because this is just a constant. So you get r prime minus 1/20 r is equal to, over here, 50 over 10 would be 5 e to the t over 30. So our integrating factor, well, okay, it's the minus 1 over 20. We integrate that. And we say, well, that's minus 1/20 t. So our integrating factor is going to be e to the minus 1/20 t. And that's what we multiply on both sides. So updating, we have e to the minus 1/20 t times r prime minus 1/20 e to the minus 1/20 t times r is equal to 5. And then we have, okay, so we'll have to do a little bit of math here. I know, you're like, math, Steve, us? Yeah. I know. All right. So we have 1/30 and 1/20. So 1 over 30, subtract 1 over 20. Well, this is the same as 2 over 60 minus 3 over 60. So that's 1 over 60. So, okay. So we end up with 5e to the minus t over 60. All right. The left-hand side is nice. And I know I keep saying that, but I want you to remember it. I want it to be emblazoned in your head. All right. When we do this process, we always end up with a nice left-hand side. All right, good. I'm going to remember that. So it's the derivative on the other side, 5e to the minus t over 60. That's also actually not too bad. We integrate both sides with respect to t. We say, all right, integrate. And we have e to the minus 1 over 20 t times r is equal to, well, here we'll have 5, and then we have to divide by minus 1 over 60, which is the same as multiplying by 60. So it's actually a big number, minus 300 e to the minus t over 60. And then, of course, a plus c. Now, let's go ahead and figure our initial conditions. So we know at time 0, there's nothing there. So if you plug in 0 in for r and 0 in for t, you'll get 0 equals minus 300 plus c, which says c equals 300. All right, well, we're almost there. Okay, multiply both sides through by e to the 1 over 20th. And what we'll have is we'll have that the retirement account at any given time is going to be equal to 300 times e to the 1/20th t. So that's there. And then subtract 300 e. And now you have to say, well, what's 1 over 20, 1 over 20 subtract 1 over 60? Well, all right. We'll figure that out too. So 1 over 20 subtract 1 over 60. Well, that's 3 over 20 subtract 1 over 60. Sorry, 3 over 60 subtract 1 over 60, which is 2 over 60, which is 1 over 30. All right. So we have e to the 1 over 30t. Okay, and now the last thing is we plug in 45. So our answer will be 300 e. In fact, we can go ahead and pull out the 300. 45 divided by 20. Well, they both have 5 as a common factor. So 45 divided by 20 would be like 9 over 4. Then subtract 45 over 30 is 3 over 2. And whatever that turns out to be times thousands. Let's go check that out. All right, so if you plug it in, it turns out this number is 1501.81. But remember, these are in thousands. So it means $1.5 million. Now, of course, that sounds pretty good right now. With inflation, who knows? Maybe you can buy like 2 Big Macs. No. Who knows? But that's not bad. Definitely doing a little bit better than some of those art history majors do. So, all right. Good. Our next problem is going to ask us to solve y prime plus 2 over ty equals e to the t. So let's start working. In fact, it's really well set up for us. There's not a lot of surprises here. We say, hey, perfect. We integrate that. The integral of 2 over t will be 2 natural log t, which is the same as natural log of t squared. And so we say, all right, well, that just means our integrating factor, our rho of x, if you will, which is e to that, is going to be t squared. So multiply everything here by t squared. We get t squared y prime plus 2t y equals t squared e to the t. I think I see where this problem is going. Here, they just want us to have a little bit of practice doing integration by parts. Because the left-hand side, of course, we say this again and again, it's nice. The right-hand side, well, it's going to take some work. We're integrating both sides. And, all right, well, this will become t squared times y. So over here, we have integration by parts. So the idea of integration by parts, we can write our formula down here in the corner, is the integral u dv is equal to u times v minus the integral of v du. Okay, so there's our formula. And the punchline is there's one part that you pick, you're going to differentiate it, and the other part, you're going to integrate it. Now, of course, you have a choice as to which part is which. And oftentimes if you have e to the t, because e to the t is so easy to integrate and differentiate, it's oftentimes the one that you choose to integrate in the hopes that the other one simplifies. Anything that simplifies under a derivative, which includes any polynomial, that's our u. So we begin. So we're going to say, here's our u, here's our dv. So our du is 2t dt, and our v is e to the t. So we would have uv, t squared e to the t, minus the integral v du. So that's 2t e to the t dt. You're like, great, now what? Well, integration by parts again. That's right. We keep going. It's one of these onion problems. I like to use that to say a problem with layers. And of course, there might be a few tears involved by the time we reach the end. So u dv du is 2 dt. See how it's simplifying? T squared, then 2t, now it's down to 2. And v is e to the t. Now, here's a part where a lot of people miss something. See that minus? Gotta be super careful. So we're gonna save our points because we want to get them all, and we're gonna put a parenthesis here to save it. So that's uv 2t e to the t subtract integral v du. So 2 e to the t dt. And, well, okay, cleaning that up, we have our t squared e to the t. We can put this minus through. Minus 2t e to the t. Put this minus through, so that'll become a plus 2 e to the t. And, of course, don't forget, after all that work, a plus c on the end. Because we want to make sure we get all our points. After all, that's what we're after. All of our points. Now, we're not quite done. That's t squared times y equals that. So we can say that y is equal to, we just copy the whole part on the top. And, well, patience, right? Over t squared. Why not? Perfectly valid to do that way. And there we go. That's it. That's the answer. Nice. Nice. Our next problem. Let f of t be piecewise defined as follows. F of t is 1 if we're below 1, and we're t if we're above 1. So if we were to plot this, which, hey, we have plenty of paper, well, I hope we do, it says what? Well, our function is always constant, and then it slants up. So we have 1 here. So we're 1, and then we go up. So this function, it's not a bad function. It's continuous, but it's what we would call, in some sense, piecewise continuous, in that we've defined it in different parts. And so this is our first time having to deal with a differential equation with a function where the behavior changes at a point. So it's going to be interesting to see what happens. But we'll get to that. We'll get to that. All right. So our problem. Solve t squared plus 1 x prime minus 2tx equals t squared plus 1 f of t, given that x of 0 is equal to 2. All right. All right. So here's what we're going to do. We're going to actually solve this twice. So we're going to say, okay, look, we're starting out at time 0. So we're going to solve it first for f of t equals 1, and that'll carry us up to time 1. And then we'll figure out what to do for time bigger than 1. So let's, for now, we'll assume that our time is less than or equal to 1. So this will just help us, because what? It means that this f of t is just 1. All right, so we're going to run through our process. We have to make it linear, so we have to divide by t squared plus 1. So we have x prime minus 2t over t squared plus 1 times x is equal to 1. All right, so we need to do our integrating factor here. So we have, this is our integrating factor. And all right, so here's our p. Don't forget the minus. It's easy to forget that. So let's not. All right, so we're going to integrate minus 2t over t squared plus 1. Now this is an integral we've been doing a couple of times, so let's just say it out loud. U is t squared plus 1. du is 2t dt. So it's du over u with a minus. So this becomes minus log t squared plus 1, or if you like, this minus goes in, this is the log of 1 over 1 plus t squared. All right. Good. Now, with that in place, our integrating factor, which is our rho of x, will be what? Well, our rho of x is going to be e to the natural log of 1 over 1 plus t squared, which will be 1 over 1 plus t squared. So that comes up to there. Okay. So we now have, what will happen? Well, okay, we'll do it in slow motion just to get good habits. It's good to get good habits. Lots of copying going on. That's all right. It's good to do lots of copying if we get the points. And don't we want the points? Yeah, we want the points. So the derivative, we have 1 over 1 plus t squared times x, and that's 1 over 1 plus t squared. We integrate both sides with respect to t, and what will that give us? Well, on the left-hand side, we have 1 over 1 plus t squared times x equals, over here, we're going to have arctangent of t plus some constant c. And, well, we're told x of 0 equals 2. So we plug in t equals 0, x equals 2. That tells us that 1 over 1 plus, because 0 squared is 0, times 2 equals arctangent of 0 plus 2. Sorry, plus c. I was getting ahead of myself because arctangent of 0 is 0, so c equals 2. Okay, so now we know what c is, and we can solve for x. So we have that, we'll say for x less than or equal to 1, we have that x, not for x, for t. For t less than or equal to 1, x is 1 plus t squared times arctangent of t, and then plus 2 times 1 plus t squared. Okay, good. Pause and catch our breath. Now, where do we go next? Here's where it gets fun. We had an initial condition at 0, and now we have the full behavior up to 1. Now, we don't know it past 1 because the right-hand side changed. So here's what we're going to do. We want to essentially glue our two parts together, because we haven't done the part above 1 yet, but we know what happens up to 1. And so to help us do our gluing, we say, hey, what happens at time t equals 1? Well, we get that x of 1, we work it out, is equal to 1 plus 1 squared, which is 2. Arctangent of 1 is pi over 4. And then here we have 2 times 1 plus 1, which is another 4. So we end up with pi halves plus 4. So now what we'll do is we'll move and say, okay, we're going to rechange our problem, and we're going to go for a time above 1. Okay, so here we go. Let's write down what's going to happen. All right. Whoops, let me find a good pen. All right, I've got a good pen here. All right, a good pen. So we'll do it upstairs here. So for t greater than or equal to 1. Okay, so now, so we've done t less than or equal to 1. We're going greater than or equal to 1. Now here's the fun thing. What changes? Well, the only thing that changes is this f of t part. So we still have it's x prime minus 2t over t squared plus 1 times x equals now t. So in particular, the computation of the integrating factor is not affected by the right-hand side. So it's the same integrating factor. So we run the process and say, oh, we still multiply by 1 over 1 plus t squared. Oh, great. So that we come down here, the only thing that changes is this part now. It's not 1 over 1 plus t squared. It's t over 1 plus t squared. So in particular, we can say, all right, the derivative of the left-hand side, it is the derivative 1 over 1 plus t squared x is equal to t over 1 plus t squared. That's the only difference between the two as far as this step goes. The other difference being we have to switch to a new initial condition. All right, well, that was part of it. We still have to integrate. Okay, well, no big surprises. Here, if we put a 2 and a 1/2, we can see, this is like u is 1 plus t squared, du is 2t dt, so it's a log. And so this would tell us that 1 over 1 plus t squared times x is equal to 1/2 log 1 plus t squared plus some constant d. Now, how do we figure out our constant? That's how we figure it out. All right, so when we plug in t equals 1, this is the value for x. All right, so 1 over 1 plus 1 squared is 1/2 times this part. So 1/2 times pi over 2 plus 4 is equal to, and here it's 1/2 log 1 plus 1 squared is log 2, and then plus d. And so, of course, we can move this 1/2 log 2 to the other side, but the point is we can now solve for d. And once you have d, well, you multiply across. And so our other part of our answer is as follows. So for t greater than or equal to 1, excuse me, we'll have that x is equal to 1 plus t squared times this part, 1/2 log of 1 plus t squared, plus this crazy constant, which you can write as pi over 4 plus 2, distributing the 1/2 through, minus log of root 2. This is 1/2, and then it comes across as a minus. And that's the value d, and then don't forget that you're multiplying that by 1 plus t squared. And there we go. That's it. That's the answer. And so that's how you deal with something that's piecewise. You basically break it up into pieces, and you say, all right, let's start the differential equation. We run the solution. We say, okay, now we're at a new point. We got to record our value, start a new differential equation, run that solution with the new value, and keep going. So you can imagine if there's many pieces, this can be like, this is going to take forever. We will develop technology at the end of the semester, which will make things a little bit easier. But that's for the end. For now, well, we keep going. Well, let's do another mixing problem. A small 10-gallon tank initially is full of brine, which is salt water, with 20 pounds of salt. Brine, which has 1 pound of salt per gallon, is being pumped into the tank at a rate of 2 gallons per minute. At the same time, the well-mixed brine in the tank is being pumped out at a rate of 3 gallons per minute. Determine the amount of salt that will be in the tank when the tank is half empty. Okay, so it's a smaller tank, but that's okay. We don't have to draw it too small. So here's our tank. Draw our picture here. And we know it's a 10-gallon tank because it says it's a 10-gallon tank and it's full. And All right. We also know that there's fluid coming in and there's fluid coming out. So we're going to draw our picture here. Fluid coming in, fluid coming out. So we'll quickly add in our parts. There's our inflow. And over here is our outflow. And in the tank, we have some amount of fluid. Okay, and it's being well mixed. All right, well, let's make sure we have all of our information here. So, when it comes to what's coming in, we know it's 2 gallons per minute, and that's in terms of the mixture, the brine, the salt water, and there's 1 pound of salt per gallon. So 1 pound per gallon. All right, good. And our outflow, well, our outflow is 3 gallons per minute. So in this case, there's less coming in than going out. So the water level is sinking. And in particular, we say, well, okay, if our water level is sinking down, we can say how much brine, fluid, is in the tank at any given time. Initially, it's 10. Every minute that passes, we lose a gallon. So the brine in the tank at time t, and in other words here, time is how long we've been going, is 10 minus t. That'll come up in our equation. It's important to know how much fluid is in the tank at any given time. That does play a role. So let's start piecing things together. What do we know? Well, if we let S of t be the salt at time t, we are told S of 0, because we're told initially it has 20 pounds of salt. So S of 0 equals 20. We know what we want to find. We want to find the amount of salt when the tank is half empty. So it started at 10. To be half empty, we want to be at 5. Every minute we lose a gallon, so we're looking for S of 5. Okay, so we know our initial condition, we know what we're looking for, at least as a time. The last thing is what's happening to the salt. So how is the salt changing, S prime? Well, salt is coming in. We know how many gallons are coming in each minute. We know how many pounds of salt there is in each gallon. So we say, all right, the inflow is 2. So this is the salt being added. From that, we also need to take the salt that's being removed. So we're going to subtract, and now what we do is we say, okay, what's the proportion? So we say how much is leaving, how many gallons per minute flow out, versus how many gallons are there total. That varies with time, so it's going to be a function involving t. So 3 over 10 minus t. And now that's the proportion of salt leaving. To find the total amount, we have to multiply by how much salt there is. So 3 over 10 minus t times S. This is our outflow. And now, with that done, our problem is set up. And away we go. So, well, we're not going to go away. We're going to solve it because we need practice. Practice is good. So S prime plus 3 over 10 minus t times S is equal to 2. And so our integrating factor, well, we integrate 3 over 10 minus t. All right, now here is a place where if you're not paying attention, you might lose something. Now you know, like, ooh, wait, Steve is pausing dramatically. All right, I'm not going to mess anything up. What's the integral of 3 over 10 minus t? Now, you probably want to say log, and that's good, because you do want to say log. But here's the part. that minus sign affects your answer. So be careful. So there's actually going to be a minus 3 log 10 minus t. So the minus sign here is because of the minus sign there. Or if you like, this is log of 10 minus t to the minus 3 power. All right, well, from here, we say our integrating factor, our rho of x, is e to that function. So, and oftentimes, it's not surprising we see logs show up frequently here. So e to log undo each other, so we can think of this as 1 over 10 minus t quantity cubed. All right, so we go through, multiply both sides by 1 over 10 minus t quantity cubed, and what will we get? Well, we'll get s prime over 10 minus t cubed plus 3s over 10 minus t to the 4 equals 2 over 10 minus t cubed. I'm going to go ahead and write this as 2 10 minus t to the minus 3, just because this part I actually have to work on the integral. This part's a freebie. And we say freebie because we know that it's a derivative. In particular, it's a derivative of s over 10 minus t cubed. And where is this coming from? Well, okay, it's our integrating factor times our function we're looking for. All right. Now, you could do various things, I should point out. You could change it. The 10 minus t, you could pull a minus out. Just be careful. Be careful. The right amount of careful. And so there's ways to deal with it. We integrate both sides. All right, well, move up to the corner. So we have s over 10 minus t cubed. Here, we follow the rules. You'd add 1 to the exponent, so that would be a minus 2. And so we'll have a 10 minus t to the minus 2. And then you divide by that, so 1 over minus 2. And then we remember we've got to account for the minus on the inside. So it really ends up being a plus. And there's a plus c. All right, multiplying through, and what do we get? Well, we get s is equal to, so we're multiplying by 10 minus t cubed, 2.5 cancel. So we get 10 minus t to the 1, 3 minus 2 is 1, plus some constant c, 10 minus t cubed. All right. Well, we need some initial conditions. We know at time 0, there's 20 gallons. So we have that 20 is equal to, and 10 plus, here we'll have c times 10 cubed, which is 1,000. Oh, that's a lot. Well, a little bit. And, okay, great. Well, you subtract 10, divide by 1,000. SSC is equal to 1 over 100. All right, so now we have our function for s. And then the last thing is we say, look, we want to find s of 5. So our answer is s of 5 is equal to 10 minus 5 is 5. Then we have plus 1 over 100. And then we're going to have 10 minus 5, which is 5 cubed. Now 5 cubed is 125. Divide that by 100, it's 1.25. And so add 5, you'll get 6.25. And so that's how many pounds of salt we have. Done. All right. Wow. got kind of lucky at the end. The fact that we're dividing by 100, it's really easy to turn 100 into a decimal point. And of course, if we want even more precision, we can add some zeros here, and I'm like, wow, that's even more precise into how much salt there is. Amazing, yeah. Well, not really. I haven't really done anything, but there we go. Now, is there anything that we should make a comment on? Does it make sense? Well, I think it makes sense. I mean, what's happening here? We definitely are going down. You'll notice at time t equals 10, what happens? There's no salt. Well, why not? Because there's nothing left in the tank. It'll be completely empty at time 10. So that's good that when we plug in t equals 10, we get 0. It's also intuitive that as we lower it, the amount of salt should go down. Now, what's one other thing that we might say? Well, currently you'll see that the tank, initially, there's 20 pounds of salt for 10 gallons. So that's a ratio of 2 pounds for every gallon. What's coming in has only 1 pound per gallon. So the water in the tank is more salty than the water coming in. So after a few minutes, the water should become less salty than where it started because you're mixing in fresher water. So if we had only just drained the tank halfway, we should have 10 gallons. A 10-gallon tank. There's 5 gallons left. We'd have 10 pounds of salt left. But because we mixed in water that was not so salty, it's less than 10 gallons. So that matches our intuition, which means I think we did it right. 2 thumbs up for us. We're great. So let's do one more problem. A tank contains 40 liters of fluid, which initially contains 5 liters of compound A and 10 liters of compound B. At time t equals 0, a valve opens up that continuously pumps in 4 liters of fluid, which contains 2 liters of compound A and 1 liter of compound B into the tank. At the same time, a second valve opens up that continuously pumps out 4 liters of the well-mixed fluid. Determine the time, t, at which the amount of compound A in the tank equals the amount of compound B in the tank. So this is a different kind of mixing problem in that we don't have just like, well, we have this one thing, salt. What's happening to the salt? We have like these 2 things going on at the same time. So this should be twice as fun. That's how I interpret it. All right, so let's draw ourselves a picture, just so we can sort of start to be like, what's happening? We have our tank here. We are going to have things coming in, and we're going to have things coming out. And, of course, as with these problems, what comes in is not going to always be the same as what comes out. Our inflow and our outflow need not be the same. All right, so we have that. And in the meantime, we have our tank here in the middle. So here's our tank, and we're mixing things up. Now let's talk about what's happening. Well, first off, what's happening with our inflow? Well, so for our inflow, we are going to pump in 4 liters of fluid. So we're pumping in 4 liters. We have, of that 4 liters, we have 2 liters of that is A, and 1 liter of that is B. So that's our in. On our out, we have 4 liters. In other words, what comes in matches with what goes out. So the tank level doesn't go up, it doesn't go down. So we say, aha, there's always 40 liters total in the tank. It never changes. But what can go up and go down is how much there is of A and B. So let's think about what's happening here. So let's make some functions. So I'm going to let A of t be the amount of A. It makes sense. And then we're going to do a similar thing. We're going to say, well, what about B of t? Well, yeah, that's what you think it's going to be, the amount of B. And if we write down our initial conditions, well, we have that A at time 0 is what? Well, it initially contains 5 liters of compound A. And that B at time 0 is 10. So notice what's happening here. Initially, there's more of B than there is of A. So this is B, this is A. But when you look at what's being pumped in, there's more of A than there is of B. And what's going to happen, whenever you continuously pump in the fluid, in the long run, this tank will look like what you pumped in. It's going to match your inflow. Let time go for a very long time, you will exactly match at infinity, of course. Well, of course, you'll get there. But you will be super close. So initially, there's lots of B compared to A. But as we pump in, there's more A than B, and so they're going to switch places. So there's a time somewhere, a sweet spot, if you will, where there's going to be exactly the same amount of each. Now you might say, how do we do this? Well, we've got to figure out what's happening to A and what's happening to B. So that's 2 equations. Let's work them out. All right, so let's start with A. What is happening to A? Well, we know it's coming in at 2 liters. So we get A prime. The inflow, the addition, is 2. The outflow is what? Well, we always lose 4 liters of the whole tank. There's 40 liters total in the tank. So we're losing 1/10 or 10% of the tank gets emptied at every minute. So 10% of A gets out, 10% of B gets out, 10% of everything gets out. So it's 4/40 A, or 1/10 times A. All right. Well, from here, we just start moving things around. So that says that A prime plus 1/10 A is equal to 2. We find our integrating factor. Well, it's e to the integral of 1/10 dt. So that's e to the 1/10 t. So when we multiply everything by e to the 1/10 t, the left-hand side will become e to the 1/10 t times A, the derivative, which should be 2 e to the 1/10 t. All right. Well, now what do? Well, we integrate both sides. We get that e to the 1/10 t times A will be equal to, here, 2 divided by 1/10 is the same as 2 times 10, which is 20 e to the 1/10 t plus c. Or we get that A is equal to 20 plus c e to the minus 1/10 t. All right. Now, so that's A. But we have to figure out what's C here. So the last thing is we know what happens at time 0. And so we can say, aha, at time 0, we have that 5 is equal to 20 plus C. So that tells us that C is minus 15. So A is 20 minus 15 e to the minus 1/10 t. Good. Now, a couple of things. We know it matches at time 0. Let time run for a long time. How much A are we going to end up with? We're going to end up with 20. So in other words, half the tank will become A. Does that match? Yes. You see, half of what's being pumped in is A, In the long run, we should match with what's being pumped in. So in the long run, we should have half of it. So good. This matches our intuition. Good, good, good. Now to our second one. So let's do our similar computation, but now for B. So what is B prime? Well, our inflow is 1. And again, 4 is going out of 40. So 4 liters out of 40 liters exits. So 1/10 of everything exits. So we lose 1/10 of our B. You'll see it's like, wow, this is basically the same. Because, yeah, it's basically the same. So we end up with B prime plus 1/10 B is equal to 1. So we can just follow this part here. And if we trust what we did, and we do, we'll have the same integrating factor. We'll get to the same point, except this 2 is a 1, which means that when we come down to here, the only difference is where you see this 2 it became a 1. So, ... we get that B is equal to some constant, well, 10, plus some constant D, e to the minus 1/10 t. And now we have to solve for this constant D. Well, we use our initial condition, and we say, well, okay, so 10 should equal 10 plus D. But what do you notice? D is 0. So that says, actually, in the tank, the amount of B never changes. And now that we say that out loud, it's like, well, of course. Because notice that initially 1/4 of the tank is B. And in the inflow, 1/4 of the inflow is B. So as far as B is concerned, what's coming in matches with what's still there. So it's not going to change. Perfect. Well, that makes it super easy. And so now we're just a hop, skip, and a jump away. Because what do we need to do? Well, we have A, we have B. The question is, when do they match? So we compare these two. So our last step, our final computation, if you will. We have that 10 equals 20 minus 15 e to the minus 1/10 t. We can add 15, we can subtract 10. So that says 15 e to the minus 1/10 t is equal to 10. All right, subtract, moves things around. Divide by 15, e to the minus 1/10 t is equal to 2/3. 10 over 15, pull out a 5. Take a natural log. You get minus 1/10 times t is natural log of 2/3, which, by the way, is minus the natural log of 3/2, because if you flip, you put a minus in front. And so our final answer, we'll put it here because we're running out of space everywhere else, is that at time t equals 10 times the natural log of 3/2, lo and behold, that is the instant in time when the amount of A equals the amount of B. Now, can we say how much there is at that time? Yeah, they both have to have 10 at that time. So that's that problem. Good problem. I actually kind of like this one, to be honest. I wouldn't mind doing problems like this again on a future test.